Valerio Lucarini. He did his PhD in physics in 2003, and you didn't tell me where, but...
Yes, in Finland. I took a PhD in Finland.
In Finland?
Yes.
Okay. In Helsinki, yeah?
No, University now of Eastern Finland. No, it's called.
Eastern Finland?
Yes, in the lakes, basically. In the lakes.
Oh, in Jyväskylä, yeah?
Joensuu. It's near Jyväskylä.
Joensuu, yeah. Right, okay. Okay, so that's what it is. And so he's giving also a talk tomorrow at MISU, the Meteorology Institute, at 3 o'clock, so we will have no talk during that time, so we can walk over there. And that one will be about thermodynamics of the planet.
Yes.
So that might be of interest to a number of us. But today he will be talking about the impact of stochastic perturbations on deterministic dynamical systems, if you're happy with the screen.
Changed, I think.
Would be better, yeah. Why sort of? I mean, I'm not for markers, though. Actually, I'm against them. So
what do? We have, of course, is
just give me a key and we move it.
itself. My machine has a virus, so everybody is getting.
It's coming.
So then we need to clean the stick afterwards.
So, I start where we sort out this is the projector.
And then get this one.
Yeah, but I need also something to transfer
What?
the talk.
I thought that was a talk.
Now this is the
that's the control.
controller.
Yes, yes. So how are you going to do that?
That's with
the
USB stick.
As I said, the stick afterwards has a virus then.
Okay, here we go. So
Because my computer has a virus, which copies itself onto every other machine.
you have a virus?
Maybe I should announce, I'll give a talk at 3 o'clock in MISU today.
Oh, this I didn't have on my schedule yet. Interesting. Okay, thank you for letting us know. And
it's on Danske Østgø events on rapid climate change.
Yeah.
On tipping points.
And you're talking about the same topic also during the conference here? Did I even ask you?
I don't think I'm scheduled for anything. But I can.
No, I think you would be, and that is on Wednesday, I think.
Oh, did I submit an abstract? Maybe I did. No, but I'll talk about something else.
Okay.
So wait a second. So Wednesday morning,
The problem is that you have the Linux.
No, I have over
we have an embarrassment of riches. Wasn't I going to talk Wednesday morning?
Wednesday. You're talking Wednesday
You're Thursday.
on... No. I think that's Wednesday at 13:30.
Oh, in the afternoon.
Yeah.
Oh, okay, fine, whatever. So,
But here.
yeah.
Yes, that's part of the...
But you're also talking in Uppsala, right?
Yes.
Yeah, I'm talking
All the time. Even when you're not talking.
but about different things.
Yes.
You know, I don't know enough about one thing, but about it all the time.
Yes, it's
So,
F.
should we see it from here first of all?
Yes. And then it's.
No, I actually think the talk at the beginning of the Wednesday afternoon we have not heard yet. I'm not sure.
Kingsley, yeah, that's it.
Some
Yes,
version
it's the first one. You should.
Sometimes
Yeah,
it's
yeah.
the same
So
talk.
this is this virus stuff here, which you now have.
Okay, good to know. I always have some threats, but they are never serious.
No, this one is also not serious, but it's but people find. Oh, now it's even this one is.
Okay, so
So it might be the projector.
Projector. I start to suspect the problem is there.
But first of all, I should, of course, what is even going on?
This is even worse, I think. It makes me feel sick.
Where's the projector? In your room?
Yes.
The other one.
Let's go again to the PowerPoint. Let's see how.
First of all, it's.
I think that. So try to open the PowerPoint and let's see how it looks like. No, I mean that is the. I think
We have a projector problem.
yes. So
Okay, interesting.
Yeah, a new one is coming. Another one.
yeah.
Okay. Wait, we can then go back to your computer.
Yeah.
Somebody with a Macintosh can clean this one. I mean, if you put it into Macintosh, then nothing happens. You can remove it. But if you put it into your machine, it copies itself already into all other devices.
Ah. Okay.
Give it to somebody with a Macintosh. Who has a Macintosh?
Down there. See Macintosh down there. More or less.
Maybe there's two files. One is called virus removal and something else.
It's a contamination. I admit that. I don't know.
This one is not clearing.
There is no speaker because there is no signal from the computer.
Yeah. So maybe there's
Okay,
something else.
it's not a loose
By the way, we do have a problem with the power. For example, the light doesn't work here, so that might be...
Is it a loose connection in the cabling between the laptop and the projector?
Exactly. That could be.
No, it's very tight actually. Even that is not a problem here. I'm not here. I left this is my some troubles.
Don't you have a minute to do
It does make you nostalgic for the times of the blackboard and
Yes. I always find it amusing when this happens in big conferences when this schedule is so strict and then it's a disaster. Like people go berserk as if I don't know.
So you're lecturing us.
Now he's not giving any bad signs.
I know.
He must have some problems when connected to the computer because his own the beam seems to be okay. I mean, when they are the lamp is very old, sometimes they sound thicker on their own.
Doesn't have power.
Someone we can.
Yeah, please.
Yeah,
Sorry,
so much
Engineering design.
Maybe you just give a whiteboard lecture.
yeah, that's
well, that's why I was telling you.
yeah. It might be
Go and you print your presentation on slides, and then we take the overhead probe.
No, I think we can stick with the slightly flickering presentation. Otherwise, it's like we all know that when you print on slides, there is always a problem. One slide is burned in the printer machine.
But since then, it's been professional.
Well, the problem is that these days nobody believes you anymore if you just do it.
No, it's wrong. Yes, yeah, of course you're doing this because you're hiding some mistakes. And, it's a sketch. But as I find it amusing when one prepares a presentation, sometimes you copy formulas and maybe you discovered after a few years that there was a mistake in the formula, like a sign or something. Okay. So, the problem is in the case. Let's see.
Alex is 2007. Before that, there was a down.
Okay.
There's logic and just
This is it. slides. Come on, let's stick to this. It's really easier. Let's say that it's better than before. Let's assume it's better than
So
before.
you want to do it with this?
Yeah, I think it's
This one should of course work.
Why don't we have enough power? Yeah. This is really strange because I know nothing about waves.
I didn't
Because
know
this is
that.
too close. It must be-
No, let's keep stick with this.
Okay.
We have all had TV in the time of non-digital era, so where there was like
Although I learned a lot.
the fog.
Okay.
Okay, so good morning, and so in the technical problems, as Michael was suggesting, should put you in the right mood for this presentation. So basically, as what we're going to do here is to look at one side the deterministic dynamical systems and studying somehow trying to find some results on how the statistical properties of these systems are changed when we add stochastic noise. And of course you can see it in terms of in a more major theoretic point of view, or if you prefer, more in terms of the properties of observables. That depends how you want to look at this problem. So let's first just briefly see some motivations of this work. Of course, in this stage, when we talk about stochastic forcing, we have immediately a bare rings that is in many fields of science, in a more or less indiscriminate way. Numerical models are taking advantage of adding stochastic forcing to the more traditional deterministic models of some nature or social phenomenon, and somehow this adding the stochastic forcing has various goals. On one side, we are trying to represent, this is the original motivation, the spatial and temporal scales that we are not able to resolve, and of course there is an entire world of recipes to define the stochastic forcing that tends to mimic these scales, and that's a huge sector, of course. On the other side, another idea that another positive aspect of using stochastic forcing is that somehow we have the feeling that by adding noise we will be able to explore the attractor of the system in some shorter time, because noise provides some mixing. Of course, it will change some of the properties, but also it will have this useful effect, and this is very desirable when we have computational limitations in terms of times. So stochastic parameterization, as an example, are more and more used in climate science, because we are basically dealing with these problems, and this has been, whereas somehow this started originally in models of very low degree of complexity, so that's somehow one of the first ideas in this direction was the one by Hasselmann. Then this has been developing into applications also for full-blown GCMs when we want to look at very small spatial and temporal scales. Of course,
Can I just ask, is there a theorem that tells you that you're sure that you get the mixing?
No.
No.
Sure that you get the mixing. Well, yes, in the sense that the idea is that you manage to get rid of, as an example, some pathological solution, for sure. That's one of the issues. And this is more comes from, you surely, once you have noise, you have, you change a little bit the statistical property. This is what we're going to say. But if you want, you tend to select, this is the point, the physical measure of the system. I will discuss about this a little later. Yes, but it's not so black and white, of course, because as soon as you have noise, the system changes, so it's not the same system as before. But, it depends how you want to see the problem. As I said, the fundamental reasons why it is interesting to add stochastic noise is that on one side, we have that once we have a dynamical system, the so-called physical measure, invariant measure, is robust with respect to introduction of noise. So this is the old Kolmogorov definition of invariant measure, of the physical invariant measure. And as I said, we get rid of the pathological solution like an unstable fixed point or something like this. And the problem is, if I go in the limit of zero noise, do I get the statistical properties of the deterministic system, or do I have a singular perturbations? As soon as I have noise, of course, in the case of pathological solution, I have a singular perturbation, as an example. In general, no, once exactly I am in this measure. This is the point. And another interesting property is that whereas once we have a chaotic deterministic system, the invariant measure is singular, in general, once we have noise, we smoothen out this measure, so we have something that from the point of view of mathematical application, of mathematics in general is very useful. We get a smooth invariant measure that is absolutely continuous with respect to the method. So, I mean, this is a huge aspect, the huge field, of course, and there are many, many different aspects. I'm just tackling a little point of view, and of course also in this room there are people who have been working on this. I'm trying to address a specific problem. So the title talks about the stochastic perturbations and the deterministic dynamical systems. And another aspect, the aspect that the way we are trying to address the problem of stochastic forcing is by studying it formally as a perturbation to the deterministic dynamical system. So we have to see whether there is a consistent way to treat, in general, the impact of perturbations to a given dynamical system. So, in general, of course, the problem of studying the response of a dynamical system to perturbation is more general than, is a wider topic than that of addressing specific stochastic forcing, and is a very, very broad class of problems, constitutes a very broad class of problems in maths and physics and whatever you want to look at. And of course, it's a huge interest, and in principle, it's a sort of a graal of when studying chaotic dynamical system is to understand whether we are able to find a closed formula or a good estimate of how the statistical properties are modulated by changing some parameters of the system or adding perturbations. And of course, only in very special cases we know the answer. And yes?
I'm a bit confused now.
Yes, please.
So,
I am also.
So are you talking about noise as dynamical noise, where you have the feedback of the stochastic perturbation in the dynamic system, or noise as in the additional, additive noise, where you have something separate from the system, so you can reduce the noise and have your dynamical system there? Or you're talking about both?
Okay, this is my dynamical system, and it goes into this, just generally speaking. Okay. And this can be deterministic, if I'm considering a small perturbation, or this can be something like this, where W is a Wiener process. So it can be a noise. This is the simplest case I'm considering. Okay? So I can modify my dynamical system with a forcing, which can have a generic spatial pattern and can be modulated by something which can be deterministic or can be noise. Okay? So in this sense, studying how the statistical property of this system are related to the statistical property of this system is, of course, a very interesting problem. And of course, what we would like, and what is a perturbation theory, which is what will allow us to study the transition between the statistical properties of this system and those of this system in some small parameter, which of course will be related to this forcing. So this is in general how we obtain a lot of results in sciences. And in the case of climate, there is a special interest, I think, because even as of today, we struggle a lot, not only with the actual computations, but even with the definitions of quantities like climate sensitivity and climate response. As an example, it's like always unclear in the literature when people about climate response what is unclear is what is the time range, what are the temporal pattern of the forcing, how close we are to a static response, to a time-dependent response. So in climate science, sometimes these concepts are a little not so well specified. And of course, it is in general. It belongs to this general class of problems. Okay, of course, in a lot of fields, once we study particular quasi-equilibrium system, we have a way to get partially rid of this problem. That is, we have a shortcut, which is the fluctuation dissipation theorem, which allows us to study the response of perturbations using the unperturbed fluctuations of the system. So this is, in general, this thing. And of course, this is closely related also to noise. Okay? Because in the case of the canonical ensemble, basically, the thermostat is a noise. Okay? So this is what is the context of what we are doing. In particular, if now we start to build the tools for we're going to see today. So, and I will discuss a little more on this part in Uppsala. So, in the case of quasi-equilibrium statistical mechanics, the recipe for studying all this problem, the closure of the problem in any aspect, was given basically by Kubo, among others, but he wrote several, let's say, comprehensive view papers and books on this. So, and in particular, in these 50s, 60s publications, the link between the fluctuation dissipation theorem and the linear response of the system has been elucidated quite clearly. A very good account, of course, is given in the first book by Landau in statistical physics, which was written actually about that time. The problem arises. The problem becomes much messier once we consider dynamical systems representing physical systems which are force and dissipative. So the kind of systems which we tend to like, the dirty system, and what has been elucidated recently is that the kind of fluctuation dissipation theory which gives us the shortcut doesn't apply anymore in general. So the situation is more problematic, and is there a way out? Recently, Ruel, among mostly, and without contributions by others, has been proposing a perturbative theory to study the response of a general system to small perturbations. So basically has been providing explicit formulas and some ideas, and to start the development of this kind of analysis. We follow this direction here, and we see how this can be useful in the special case where we study stochastic forces. Okay? So the goals today is briefly introduce some results of this perturbation theory. Again, this will be discussed more in Uppsala, and we will use it to study the impact of stochastic perturbations. I propose you some general properties and applications in a system of geophysical interest, which is the Lorentz 96. It's very popular, especially in the community of data simulation people, of course. And hopefully, I try to convince yourself this makes some sense. Okay, let's first put together the machinery, looking at perturbations to NES, which is not a nickname for Lochner's monster, which is Nessie, but is non-equilibrium steady state. Okay, so the mathematical context where this has been developed originally, now it's getting more general with time, is the word of axiom A systems, which are a very special class of dynamical system where we can do, if you want, where we can develop results which are of interest for physical, for applications in natural and social sciences. And of course, they are very special flows. They are definitely non-generic situations. But as we all know, if you look at the generic case in maths, you end up with very weak results. So, as a special case, they are basically generalization of Amazon flows which are hyperbolic, structurally stable. And apart, I'm not here going to all the mathematical, very important properties. What is interesting here is that these systems possess a so-called Sinai-Ruel-Bowen invariant measure, that is, time averages converge almost everywhere to the ensemble average for measurable observables. So somehow time which translate into time averages are well defined. Okay? This is a very, no matter where you start from your initial condition. So this is a very practical statement from the point of view of numerical applications. And we have well-defined statistical properties. Let's consider that every time we do simulations, we assume this is the case. Otherwise, we will never start. So it's a working hypothesis that is very useful. And fortunately, they allow us to deduce a lot of properties. Okay, and an important step is that somehow there has been some work, mostly by Galavotti and Cohen, supporting that if we consider a system with many degrees of freedom, and we consider decent observables, which are somehow macroscopic, well, we can treat the system as if it had this property. So this working hypothesis makes sense. So this is very reassuring, okay? So this is, of course, a gray area. It's not, some people wouldn't like this hypothesis, and of course, in general, the dynamical systems are not axiom A, okay? So, but, you know, this is the gray area where we have to move. So let's take it as a working hypothesis. And it is actually an extension of the ergodic hypothesis, which is used in the case of quasi-equilibrium system. So it is again in the realm of statistical physics. It's not, we are not in the general world of dynamical system. Okay, where we can do, this is the situation where we can do statistical physics. Okay, so let's. What are the properties of this measure? The crucial one is that it is singular in the stable directions as effect of the contraction, and locally, this is an expression by Ed Lorenz, is a Cantor set times a smooth manifold. Okay, so it's very smooth along the unstable manifold and singular along the stable manifold, which is MS. So it is very different from the smooth measure that we usually encounter in quasi-equilibrium physics. Okay? So this is important. This is a very different situation. Nonetheless, in spite of this difference, it is possible to develop a perturbation theory. Not what is the problem is that once I have a smooth measure and I do a perturbation, it's, I mean, somehow intuitive that I can map the invariant measure of the unperturbed into the invariant measure of the perturbed system as a sort of in a sort of a continuous and actually differentiable way. For some singular measure like this, it seems more unlikely. But actually, it can be done. So if we perturb the dynamical system by adding this additional term, we can find a way to express the expectation value of a general observable phi into basically a series, perturbative series, where the first term is the unperturbed value. So when E of t is switched off, is set to 0. Okay? And we have an infinite series, for which we have a closed formula, which is a convolution product of a Green function times the time delayed perturbation. Okay? So this is a very comfortable formula. So we have, this is a very powerful statement already, but what is interesting is that we have a closed formula for the green function where basically the whole physics of the system lies. The green function, this is I'm here presenting the general term. This is was presented in mostly in 2 papers by Ruel in 97 and 98. Has a lot of good properties. First, it is causal. That is, there are these nice theta distributions ensuring that the green function is 0 if any of its argument is negative. And it can be, this is an important thing, you see that it is the expectation value over the unperturbed measure of some operator. So it is a true perturbative theory. That is, I can compute the response only by looking at the properties of the unperturbed system. Okay? So this is where, so in principle, I do an integration, I compute certain expectation values of some operators. So you say I save the trajectory of my flow, I can compute its how its properties, statistical properties, will change by any perturbation and for any observables. So what are the elements of this function? Basically, there is the observable. We have an operator which projects on the perturbative flow, and we have an unperturbed evolution operator. So it's actually a very special formula which looks like the usual perturbation theory if we put a Hamiltonian evolution and so on and so forth. And we put here the canonical ensemble. So this is quite interesting. So let's go in the linear case, which is what often we are more interested into. So what do we have is that if we have an input I of t, which is our modulation factor E of t here, and we have an output O of t, which is exactly our first order perturbation, we have this sort of link, which is just a convolution integral. This is so we are in the usual form that of a convolution integral, and of course by applying the Fourier transform, we obtain that the Fourier transform of the output is given by the usual product of the Fourier transform of the input and of the green function, which we call linear susceptibility. So this is the normal theorem of. We are back to a very comfortable expression. So this is a linear. We have this sort of linear relation, which the interesting thing is that this has been conjectured before, but this is there is a proof that this is true. So this is very important. Okay. So what is important is that once we have that formula, we have a huge class. We have huge constraints on the green function and actually its linear transform, which is the chromospheric relation connected the real and imaginary part, because the susceptibility is analytic in the upper complex omega. And so if we have the measurement information of the real part, we can compute the imaginary part, and so on. And we will see why this is important in this specific case. And remember, this is a very general property of all linear systems. So we are in this world, which is, again, very useful. Now, let's simplify the formulas. So Phi1 of t is just a linear convolution of the green function with the modulating factor. The linear green function is something more tolerable here. And among the properties, if we can find a time Taylor expansion of the green function powers of t, we find the asymptotic behavior for large omegas of the susceptibility. So there are a lot of computations we can do. In general, the short-term behavior of the green function gives the asymptotic behavior of chi. So now, the last element of this part is a brief discussion of the applicability of the fluctuation dissipation theorem. So as I said, we have a result, a basic result that there is not, it is not possible to write the response of the system as a correlation integral, which is exactly, in the general form, what the fluctuation dissipation theorem is. The reason is that in the canonical ensemble, the system explores the smooth measure in all directions. In the case of the deterministic dynamical system, the system never fluctuates along the stable manifold, because by definition is constrained to be along the unstable manifold. Whereas if I add a forcing, it will push it out of the attractor with probability 1. Therefore, the unforced fluctuations and the forced fluctuations are fundamentally different. There is an additional term which is related, which is actually of interest, of course, for data simulation, that is the term that's related to the point going back onto the attractor. Okay? So there is this fundamental problem. Still, there are some studies suggesting that FTT gives some good results, and these have to be studied more precisely, and also from, to understand to what extent it is applicable, even if there are some fundamental problems. Okay, let's. Okay, so this is the setting of the perturbation theory that we need for this stage. And now we have noise, and let's see what happens to what I've written. Okay? So basically, what is the stochastic forcing here? As I said, we make a very simple, we can generalize this, but here I'm presenting the simplest case. So E of t, my modulating function, is just epsilon times the white noise. So the expectation value, now this is the expectation value of, in terms of the realization of the stochastic processes, of eta is 0, and of course it is it's a delta correlated noise. So it's a white noise. So now we can write the impact of this, the impact of noise, into my system. So what I obtain is, I'm writing here the first two terms. So the change in the expectation value of the observable phi given by epsilon times the linear term plus epsilon squared times, this is the second term in the Ruel expansion. Okay, now I take the expectation value in terms of stochastic realization of stochastic processes, and what I obtain is that this immediately vanishes, because it's a linear term, so it's going to be 0. So the first result is that, which is interesting, the first correction goes with epsilon squared, so with the variance of the noise, and I have a closed formula for my impact. So this is exactly the response how the statistical properties of my system change by adding a white noise. So this is a closed formula. And note that here I have an integration on the unperturbed state. So this is already a closed formula, which you can slightly be happy of. And of course we get that only even orders will appear, because given the properties of noise, of course. Of course, we will have no time dependence in my response, so I will just shift the expectation value of my observable. Okay, and again, I have a quite interesting, it's a closed expression, we can compute. Let's do some observations. As I said, the first order correction is a second order term, so it's proportional to the variance of the noise. And so in the limit of epsilon going to 0, I have actually what I would like to obtain, that the correction, of course, goes to 0. This is just a consistency check that I want to have. And the convergence of the statistical properties is quite fast. It goes with the variance. Okay? So in this sense, adding a little bit of noise is not going to alter a lot to my statistical property. And it is under control. It goes with epsilon squared. We have an explicit formula. Interestingly, if the unperturbed system has instead an absolutely continuous invariant measure, I can work a little bit with integration by parts. And what I can write is, like in a fluctuation theorem, that the change in the expectation value is given by the correlation integral of 2. The integral of the tau of the correlation integral of two observables. So this looks nice, and actually it is not so strange. Okay, now we go to second order properties. Up to now we have looked at changes in the mean value of an observable. Now we study the self-correlation of an observable with itself. So we just repeat the calculation. It's a little more tricky. So we put in here the correlation. So we have a double expansion, which becomes a little messy. And nicely enough, already the first term has a product of two noise, because there are two terms here. So the calculations are a little, it's just a double expansion. So the first order, which gives me no vanishing result, has the product of two green functions of the first order, because, I repeat, I have a product of two noises. Now I use of course, the correlation properties of the noise when I write my expectation value, and I get this funny result, where we have the first order goes again with epsilon squared, which we like, and there is this interesting integral. So there is a convolution product of the two green functions, but for some reason there is a wrong sign. You see, there is G1 of sigma, G1 of sigma minus t. The sigma, instead we want to be a true correlation integral, it should be t minus sigma here. Okay? Now, who cares? Now we compute the Fourier transform of this object. So if this were a true correlation integral, the Fourier transform of this will be given by the Fourier transform of this times the Fourier transform of this. So it will be the square of the susceptibility. By the fact that there is a wrong sign, there is a different sign, we obtain that the Fourier transform of the correlation integral is given by the square modulus. It's proportional to the square modulus of the susceptibility. And this is very interesting, because a noise property maps into a general linear response. So this is the susceptibility which applies for any class of forces. But let's try to make it more useful, because, okay, how to compute this property? Seems like a mess. Actually, it's very easy, because this property is nothing but the difference between the power spectrum of my observable, phi, in the presence of noise, minus the power spectrum of my observable without the noise. So this is a very simple thing to compute from the model simulation. I make two runs of the models, very long runs of the model, take the difference between the power spectra, and I get first, and I get this expression, which is this. First, so the difference between the power spectrum of the signal, in the case with or without noise, gives me information on the linear susceptibility. First, nicely enough, this quantity is positive definitely. So, please.
So, when you do the calculations that I mentioned, by calculating the Fourier transform, for the models that you're looking at, is it not that you get just a difference of very too wide power spectrum?
I'm sorry?
That you get a difference of very wide power spectrum? The spectrum, because you have the power spectrum for the noise, for the model is going to be wideband.
Yeah, but
and the other one is going to be also wideband, and then you're going to have a difference.
But this is, in fact, this is the power, so since it's a chaotic system, you know, this, let's say, usually it's a red spectrum, okay? So one is going to be like this, just to make it simple, okay? This is the unperturbed system. We look something like this. Once I add noise, white noise, it will be okay? This difference.
Is it always like that for any kinds of noise?
As soon as you have noise, you can prove that this is a positive definite form.
Because, because I don't see that the perturbed one is going to be such a close match to the unperturbed one.
Depends how strong is the noise.
Right.
Yeah, but if you put a little bit of noise, let's say.
Yeah, of course. And if the system is not very unstable.
No, the system is very unstable.
Yeah, that's why. So will be that it will explore more the state space, and then you have a wider difference there.
It
I
okay.
tried it, yeah.
It depends. This is in the limit of very small noise. So it can be bigger, but then you go out of perturbation theory. But anyway, the nice thing is that you prove that the power spectrum of the system with noise is for every value of omega above the power spectrum of the unperturbed system. Which makes sense.
Yeah.
I'm putting energy into the system,
Yeah.
speaking very loosely. But this is a positive definite quantity, which is very good. And it's easy to compute, because I compute the power spectrum in one case, in the other case, and make the difference, and it will look like, it must be positive for all omega, positive for all omegas, and I know that it's going to be basically the square of the modulus of the susceptibility. So, by studying power spectra, we find the susceptibility, which actually looks like a fluctuation theorem a little bit. Yeah? So, because we, from an information which is very rough, these are the natural fluctuations of the system and the natural fluctuation of the slightly forced system, we get the response, which is for any classes of perturbation. I remind you again. So, what is interesting also is that since chi of omega is, we know from the theory, from Roel, that it is analytic in the upper complex plane, also the logarithm is analytic in the upper complex plane. So we can apply a Kramer-Kronig theory to the logarithm. And so the real part of the logarithm of this, which is the logarithm of the absolute values, and the imaginary part, which is the argument, will be linked by Kramer-Kronig relation. But from the observation of the power spectrum, we obtain this. So by using Kramer-Kronig, we can obtain this, and so we can obtain this. So we find the all susceptibilities, not only the squared modulus. This is very, I think it's an important point. So we can reconstruct the linear susceptibilities only by looking at power spectra, which is otherwise impossible. Okay? As this is the property of white noise. This is why it's so good. And from it we can find the green function of my system. Okay? Please.
I just need to check here. So these results obviously depend crucially upon the forcing being white noise.
Yes.
Because you have used the correlation structure of the white noise to
Yes.
remove many terms. Now, that seems to be an interesting way to examine the properties of the system. But if we were to actually construct a stochastic representation of a system, and we wanted to incorporate the effect of, say, truncation on the fast components of the system, we wouldn't use white noise as the forcing, we would use red noise as the forcing. So is this really a statement about how we can understand deterministic systems by giving them a small amount of white noise?
Yes.
Or is this a theorem about how we model deterministic systems stochastically?
No, this is, if you want, this is a rigorous result on how, adding white noise, I explore the properties of the unperturbed system.
Right.
Then, of course, once okay, another thing is that you can add a lot of, this is the simple case, but you can instead do this, and the results are basically the same. In where all of those are white noises, which is starting maybe to become a little more helpful with any sort of a matrix of correlation. The matrix of correlation comes out. This is not a problem. Of course, once you put properties in the correlation, they will end up as modulating factor in the susceptibility, and they did not have the good analytic properties, so they can screw your system. But you can write closed formulas as an example. Anyway, you cannot reconstruct it, but this makes sense, because you can reconstruct things only when you have a fundamental property set, which is in this case the fact that you have a delta correlation. Otherwise, you would have to, actually, one thing, I've not done the calculation, but I think that in some cases what happens is if you, actually, yes, this is, if you, I know this is the case, I have still to write it down, that if you have a noise, in this simple case, if your noise has a certain structure function, okay, this thing will become, of course, an important aspect, the Fourier transform of it. And this will end up modulating your susceptibility. So if you know this, you can also do some reconstruction. I still have, I've done the calculation, I've not gone through the final conclusions, but through this, basically, you will end up somewhere in the difference between the two spectra. It would be the square susceptibility times, I think, the square modulus of that f. Okay? Yes?
When I do a simulation, I never get a smooth power spectrum like that, unless I run forever. And now you have the difference between two power spectra, and it has to be positive all the time. Will that really happen?
Well, again, it's a. You must have. One could say if it's not positive, this means that you don't have long enough integrations, or your estimate of the power spectrum is not good. Also, I think it's important to consider how you compute. How from the data you find the power spectrum, because as an example, if you use fast Fourier transform and take the square modulus, of course, is the definition, but it's a noisy way. If you use some various way, like maximum entropy method to compute the power spectrum of the huge class, you would actually quite easily get something which starts to become smooth. I will show you an example.
But in that case, since that's an approximation in itself, are you then sure that it will stay, the difference will stay positive?
I mean, again, this is all of this is true in the limit of infinite time and so on.
And epsilon going to zero, if that's the problem. I mean,
I agree.
It says that you want.
I agree.
Go to infinity and epsilon going to
zero.
but
the epsilon, I think honestly that the epsilon going to zero problem is not the expansion work actually quite well in general, at least in my experience. The problem of estimating, but that is the general problem of estimating the power spectrum. I mean, we have seen thousands of papers where people put a power spectrum of some large-scale climate phenomenon in two different climate regimes and make study whether it's stronger or weaker. It's the same problem, okay? But you're right. Of course, there is a problem of ability to represent these properties. This is true, absolutely true, and this is not something I can give an answer. This is definitely system dependent in general. But
don't you have to sort of avoid resonances, because resonances can give you dips?
I will show you in a second that actually what happens is that if you have the resonance, say in a model like this, what happens is that once you have noise, this thing will shoot up exactly there. I will discuss this with the
yeah, but don't you get wings? My question is really.
This has to be in. It is probably you get wings in sense that it becomes smaller, the absolute value, but it cannot cross zero. It cannot because this is a positive definite quality. I show you in 1 second. Okay, so let's go a little quickly on the Lorentz 96 model where we have done some of these studies. So, I mean, these are the formulation of the model. I guess you're somewhat familiar. So we have advection, dissipation, and force. And that's been used so much for data simulation, dynamical system, and now it's been used more and more in the computer statistical physics itself. So we have two parameters in this system, basically the number of points and force. So we consider two observables, the energy, the so-called energy and momentum of the system, and the intensive equivalent, so E over M, and M, small m equal capital M over N. We find from the equations a stationary state of my system, so I can do a little sort of thermodynamics of my system, and one can, by studying the steady state, you can find the simple parameterization, numerically at least, which works actually very well. Interesting is the system is extended, But in the chaotic regime, the properties are intensive, and they are very intensive to a very good degree of approximation. So we've done the simulation actually with n equal 40 and f equal 8, but we can rescale it for various values of x using this, and various values of n by using the fact that they are intensive. So it is a good model because it's a good experimental setting to start.
Sorry, what do you call intensive?
Divided by n.
Yeah, but I mean you can always divide by n. I don't understand what
It's if you change n,
you'll get the same number.
Yes, you get it. They are very stable. When n is larger than 10, that is when the information doesn't propagate too quickly across, they work well. So, as we consider this sort of perturbation, okay, simple, a modulation in my forcing. So, we consider an observable, and we can study, in the way I've said, you can do explicit calculations, you find the Green function, you find the asymptotic expansion of the equivalent susceptibility. So you get a very good, this is a very powerful thing to study the asymptotic behavior of my system. And in this case, we are even the leading order for both the real and imaginary part, but let's consider this leading order as an example. And we can reconstruct by doing a lot of simulations. That is, we run an ensemble of runs, each with a forcing a slightly different frequency. We do the analysis of the output, and we can reconstruct the susceptibility. Again, this is I'm going to talk about this more in Uppsala in detail. We can do this reconstruction, and we get the real part of the susceptibility. We can play a little bit to extend it using rigorous extrapolation based upon the analytic properties. We can do the same for the imaginary part. The black is the measured, and there is a little bit of noise. Once you play with integral relations, the noise is smoothed out. But we have noise, and this has been a very, not intensive in terms of supercomputing, but at least a very pedantic analysis one had to do. Many simulations, many ensemble members, each for each frequency we are scanning. So this has been basically a spectroscopy of my system. Okay. And from the susceptibility, I remind you that we can reconstruct by the inverse Fourier transform the Green function of the system, which projects my forcing with any time pattern, but with the same spatial, any time pattern in the future. Okay? So I can use it to project in the future my forcing, not only sinusoidal forcing. This is a simple statement of linearity. But we can reach this. This is a very important operator, of course, to predict actually the change in the statistical properties. Now, let's use our approach. So, I did this. I computed the Fowler spectrum of the perturbed system. It is only, basically I've used 100th or 1000 actually, almost, of less integrations. Only, it's 1000 ensemble simulations. That's it. Instead there it was 1000 ensemble, an ensemble of 1000 simulations per frequency scanned. So this has been only 1000 simulations, only that. And they get, this is the difference between the two power spectra, and they get this very, very smooth blue line, and the red line is the asymptotic behavior I've computed from the theory. So we had, look where we go, very, very far. Then, of course, I had some, but this is just finite length correction. This is a perfect agreement. This is the squared modulus of the very nice susceptibility I showed you before, which is not so noisy here, but this is a logarithmic scale. But when we go to the high frequency, it gets noisy relatively to in logarithmic scale. Here you can imagine this is very, very smooth. Actually, these are shifted by a factor of 10, but they are perfectly overlapping. And the same with another observable, which is the momentum. And now I go to a little bit to what we were discussing. So again, blue is what we obtain with the approach with the stochastic forcing, and black what I had obtained with deterministic forcing and the spectroscopy of the system. Again, these are shifted by a factor of 10. This is, in the case of the momentum, there is a resonance. Here. And as we see, here, there is a dip on the two wings, of course, because I have a resonance. And what happens is that getting these points right, of course, is harder. Because with the finite sampling that we have anyway, when the system, the response of the system near the frequency where is very excitable can easily create, let's say, blurs the signal to noise somehow. Because the strict positivity that I have enforced is obeyed on the average, but it has more, it has harder time somehow. Because sometimes the system has a very high power spectrum near its resonance, okay? So when I force it, on the average it will be even higher. But somehow it's not so easy. Whereas here, actually in the high frequency range, as soon as I force a little bit, the system will be very happy to have more energy. So anyway, the results are very, very much better than I expected. Again, this is the asymptotic behavior I get, which is absolutely perfect. This is the range. This is the same range I showed you. This is the same range. Okay? So here we go to 10 to the 3 after a very painful extrapolation using analytic properties and constant relation, which is the constant relation is imposing analyticity. So we got here and here just directly the system gives us a much, much better result. Okay? So this is a very comforting. So concluding, I think I'm about in time. So we basically what we have done is using the Rouen response theory to study the impact of stochastic forcing, and we find, looking at the changes in the average properties of the observable, some comforting properties which we want to have. That is, the change in the ensemble average, in the ensemble averages scales with the variance of the noise. It is a second order effect, so it goes with the second Green function, not with the first Green function. So I cannot use it to study linear susceptibility. Okay? Whereas if I study the correlations, I go back to my linear response. First, I find that the effect of any noise is that of enhancing the power spectrum of the system at all frequencies. Second, we find a link between the difference between the two power spectra and the square modulus of the linear susceptibilities. And then, using the theory which tells us what are the properties of the susceptibility, we can reconstruct this here. Okay? And we have proved this because, of course, there are many issues related to signal analysis that I'm aware of. So we tried in the case of a simple system, which still starts to have some noise, it's not entirely trivial, and the method is very efficient and very parsimonious with respect to other methods of studying the response. So this was very encouraging for practical applications. I don't know more than this. And, of course, I've been doing the analysis of what has already been done for this case, where I have more general pattern of noises, so more, a lot of, as an example of white noises, and also have some preliminary result in terms of correlated noise. Okay? And of course, there are many other ways to study in terms of noise, and I would be happy to study them, to see links. Okay? Thank you very much.
Questions, please. Yes.
I'm a bit confused.
Because
when you said that there is a forcing, and then it's like you have, in the moment where you have high frequencies, then the forcing there is going to take the trajectories of the system, or the solutions of that equation there, away from the tractor, and you're going to have more cases of just trajectories escaping. You know what I mean? It's like, I'm not used to look at the dynamical system this way, so more in terms of the trajectory. So when I see
okay.
forcings, I imagine there are going to be many solutions that are going to be unstable, and I'm not going to be interested in those. But I don't see how to see that in the power spectrum you showed us.
No,
because then if you have a forcing there, you seem that you keep them all, you are able to keep them all summarized in the by a measure of the...
But what do you mean unstable?
Unstable is that you just go away from the tracking set.
Yeah, but this is if you are near the border
So
of the
they're not
tracking
bounded
set.
anymore.
If they're not bounded, yeah, but in this case, I mean, depends how big is your basin of attraction.
So you're just trying to get forcings that you still keep.
Yeah, but I mean, if I take the atmosphere and I perturb its state a little bit, it will still, and then I let it go, it will still go back to being an atmosphere.
Right. Yeah.
Okay. So yeah, I mean, of course, the individual trajectory will diverge. This is true, of course.
Yeah.
But I'm not doing a problem of control.
I see.
I think I'm not controlling the divergence of the trajectory. This is not my interest. I'm happy if they diverge.
Okay.
Because actually then they will populate.
And also would say that your model is not good.
What do you mean is not? Depends what
No, because if you have a model that, for example, if we have an atmosphere and then we have a forcing, and then we see that it still is an atmosphere, it's because we are, we are seeing the system as a model that can represent very well that atmosphere.
Yeah, but it's a totally unstable system, of course.
Right, so...
It is unstable.
Right.
It's not
We
stable.
agree. Yeah, we agree on that. But, for example, imagine that I don't know how to write the model of that atmosphere very well, and I just choose something that doesn't really represent all the dynamical aspects of that atmosphere.
Yes.
So I do a forcing, and I'm not going to get a solution that corresponds. It's not going to be an atmosphere anymore for me, because my model is bad. It's unstable. It's too unstable.
I don't understand what you mean by unstable. You mean that it explodes?
Yeah, it is
the Earth explode.
Huh?
The Earth explode,
Is
for
there
example.
explodes?
Yeah, but it explodes in the sense that the difference between the two trajectories will increase.
Yeah, they will increase in such a point that I won't be able to...
Oh yeah, but that's okay. But when you talk about, I understand, but when you talk about statistical properties, this is what you want. Yes.
You want that?
Yeah, of course, because I want my trajectory to populate the attractor. I'm not interested...
The state is...
I think that maybe the confusion arises from the fact that you're not distinguishing between sort of trajectory, asymptotic stability and structural stability.
Yes.
That's right, yeah.
Yes.
You see, I mean, again, this is where things become a little bit more delicate, because basically what Valerio is saying is we're going to assume with Galavotti coil and so on that things sort of look actually alike, so they are in a particular structurally stable,
of course.
And so if that ain't so, then this
This
goes
is
away.
the end, of
This
course.
goes away.
Fine,
Yeah, no. If it is not structurally stable, in the sense that this is in the sense that we. I give you an example where this is actually makes sense. Again, in a climatic setting, let's say I am. But again, we have to consider large-scale organization of the attractor. So big transition. So say I'm considering the classical problem of snowball Earth. Okay, so here's the solar constant. On the abscissa, and on the x and the y I have, I don't know, average surface temperature. Okay? So here this is my present climate, and there are various studies showing that this can be bistable or might be not, but this is a reasonable setting. If I'm here, and I put noise in my solar constant, I can reconstruct, in principle, not saying it is easy to do practically, but these results tell me that I can reconstruct the response of my system to perturbations in the solar constant. Here, here, here. If I am here, still yes. But of course I have a problem of convergence of the properties. What I will have is that the next terms will be big here. Okay? When I am at this point, at this specific point, all of this doesn't work. It just makes no sense. Okay. But what happens is that here I go from 280 Kelvin to 240 Kelvin. But between here and here, like graphically, if my attractor is like this here, here it is, I will have basically two disparate bases of attraction. So the history of the system will be important. So here I have two attractors, but I am only here. Then, when I go to this point, this attractor dies, and I will collapse into the relative of this attractor here. But this is a totally different story. So I am far from this situation. Otherwise, there is no perturbation theory you can develop. It's like defining the heat capacity of water at 10 to the minus 6 degrees Celsius. Okay, near freezing point. That's where we have a divergence actually. So, okay.
Yeah.
Thank you. Yes. Thank you for asking.
Let me maybe just comment that what I will be talking about in Uppsala, but I don't know whether anybody's going to be here on. I mean, from here would be there on Friday, which is when I'm talking.
That's right. We have
is a theory. In other words, what Valerio is doing and some other people is sort of what we call the forward point of view. They're studying PDFs, probability density functions.
Yes.
We're interested in what's called the pathwise approach. We're looking at actual individual trajectories. So you need random dynamical systems. Okay. But you can find the stuff on those.
So yeah, this is, in fact, I mean, as I mentioned, this is, to tackle this problem, there are various points of view, and of course, this is, if you want, what Michael is doing is taking, if you want, the opposite point of view, where the more relevance, if you want, is given to the stochastic component, rather than the deterministic component in some sense. So it's a reverse point of view, which is actually quite very interesting, of course. Here instead, we take the deterministic dynamical system, and we say that the stochastic perturbation is a special class of a perturbation. And we hope that things work, and actually they seem to work quite well, because the only thing we need are basically this sort of properties, once we take the expectation. So again here, since you take expectation, you are doing the averaging over many realizations of the noise. You are not looking at individual trajectory. It's another game. It's as simple as that. Okay?
If we turn to sort of your sort of first statement that, that really noise is just a poor man's representation of whatever is not resolved. Say in any realistic model of a high Reynolds number flow, atmosphere, whatever. There's no such thing as the unperturbed system, right?
Yes.
So what is? How should we think of this in that case?
No, you're right. I mean, the problem is, I agree entirely. But this boils down to, I think, to another, it touches another class of problem, is the problem of studying the model error. Okay? So there is a lot of people who study the model error, which is somehow related to this. Where are we? Is there a limit? Like, we don't even have a theorem guaranteeing that if we go to very, very, very high resolution, we put everything in, we're going to converge. So the problem is, but let's say I have two representations of reality, and again, I'm using Lorentz 96 not by chance. Lorentz 96, of course, has two versions. One is the simple one I showed, and then there is the other one, which is more interesting, is where you have the slow modes, the slow variables, and which are the grid points of, let's say, synoptic scales, and then each one is coupled to meso-scale processes, which are fast, and there is a time-scale separation. So as an example, these guys talk to this guy talks to this, but they don't talk directly to each other. Okay? But they have to. They have a very nonlinear way of interacting. So, as an example, one of the first why this model was interesting was studying what happens once I add these boys here. So so what happens is that you have the average on the climate point of view, you're basically renormalizing the forcing. So one way of studying this could be what is a nice representation of noise, which leads me from this representation to the one I just showed plus noise. Okay? So in this case, this problem has been tackled in many ways. I think I will try to do this in this way as an example. So if you want, you are comparing two models in a hierarchy of models which are nearby. When you are adding another component here, it is this component here. Of course, you can do it step by step. That is, you add this all in one point, as an example. And in terms of linear response, nothing should really matter a lot. But so again, you are stepping up or down in a hierarchical ladder of models, and you try to do this. Then, of course, we don't know. The problem is that we barely know it. We don't even know what is the real model, the real system, and we don't have the exact equations. But we can think about physical systems or equations interesting for mathematical physics where we know what is the actual equation. So we can study this in a more, if you want, theoretically convincing way. Okay? Here we always face the problem of model error, and this can be seen as a way to try to tackle this. But you're right.
I mean, if we say that we know, it's the Navier-Stokes equation. Right? That's our equation. So it's but being a mathematician, it's the Navier-Stokes equation is your equation. And you don't know the invariant measure, you don't know any of the unperturbed system. So how is it helping you to add noise to the Navier-Stokes equation?
Well, I mean, there's been one can say so you shouldn't do any numerical simulation, which has been the prevailing point of view in a lot of maths for many years, in fact. But if we accept our ignorance, we can try. But no, I agree. I mean, once the idea of adding noise is, I think, taken as a point of view the fact that we are ignorant.
I think we have to be very clear about this. I mean, statisticians have been thinking about this for a long time, and they wouldn't like, and I wouldn't like as a statistician, that the notion of model error, right? I mean, models as abstractions are always in error, so that's simply a tautology. What we would talk about instead is structural uncertainty. The fact that the equations that we write down, we know are an imperfect representation of the system that we're studying. And therefore the addition of a stochastic term is a subjective assessment of uncertainty or ignorance. It's not designed to be physical, it's designed to capture our limited understanding. So that's why arguments like truncation, truncation arguments and attaching stochastic terms instead of fast components, I think that is a way for us, right, as fallible humans, to find simple ways into the description of the limitations of model. So model error or model validation, they're horrible concepts that have no place, I think, in serious thought about complex systems. We should be thinking instead about subjective assessments of model limitations.
Okay, that's
of model
limitations.
No, I actually think it's a good point to try to define correctly I think this is what people do. The people study model error, but it's error with respect to an ideal model, which you don't have access to. So it's. But you're right. One should try to use the words carefully. I generally agree with this point of view, but yes.
You separated between spatial and temporal effects. I mean, the noise can also be spatial, and of course it can be coupled. You might have much more noise in high wave numbers, for example.
Yes. You can do, as I said, you can partially address, so you can partially address this in the following way, as I said. Okay, you add noise with different intensities, or with different spatial pattern, which can end with the correlation matrix that you can.
J is like wave number, yeah.
It's whatever. It's an index. So if you do a wave number representation, you can of course sorry, this is X. So you can decompose as you want. That's about a problem of model representation, moreover, but which is absolutely crucial. So and then you can do this, and is a Cij delta P minus T prime as an example. Okay. And you can address this, and you find some of the results become more complicated, but you can still address it. Of course, a step forward, which is another problem, is once you have, in general, a noise of this sort. Okay? A forcing of this sort, which can be a random field, as an example. Well, this is something we're studying now. Actually, even the theory for a deterministic forcing, once you do this, is not so trivial. There are some work, we have just put a work on archive studying this problem, and we still have to draw conclusions on the noise.
We've actually done this for Lorentz 96. We've used an Olsen-Allenbeck process to give red noise in time, and then we've used that to inject high-frequency noise in space. And the reason is that with Lorentz 96, it's basically quite linear over short time periods, and we wanted to make it more non-linear. But the non-linearity comes from the high-frequency waves, and they get damped out by the physics very quickly. So you have to keep pushing them back in. So that's what we did. I mean, we deliberately coupled a high-frequency spatial noise with a time-evolving temporal noise.
Okay.
That made the system as non-linear as we wanted it to be.
Okay, good. Yeah, that's what we should talk about. Yeah, thank you. Yeah, that's very interesting. So we have, yeah, that's good.
Well, if you want to come back to Peter's question, there are models for which are not quite non-distillers, which you can prove stuff. It might actually be interesting, like if you have the biharmonic operator, the harmonic operator, this guy did some stuff. So it actually might be interesting to try to think about Navier-Stokes as a perturbation of a model for which you can prove stuff.
Yes, one should, and then hope that some historical structural stability helps you to link to link the dots. That would be, yes, exactly.
Might be interesting.
Yeah.
Not an easy exercise.
No.
Not homework for tomorrow.
No. Take your time. Tomorrow.
Okay. So you had hyperviscosity, you mean? Hyperviscosity, but what do you mean by linear?
Biharmonic.
Biharmonic.
Fourth order.
Yeah.
Yeah.
Yeah. And why?
Well, I mean, it works. Remember the Rampos.
That is also by Cedric Vignani, the physics method, I think, that you can, if you add some of these hyperviscous operator, then you go to the limit in zero, you select some solutions. I think there are some properties one can prove, but I think it was studying Euler equation. But yes, it's a very highly technical result.
No, but the idea goes back to Laduzhinskaya in her book.
Okay. Any other questions? Or suggestions? Discuss over lunch, of course. Sometime after lunch, we can have a more informal discussion with Michael about variability of the solar radiance and associated issues. So that will be also here and roughly at 2 o'clock.
Could you do that earlier?
It was a problem of that it was
do that
cold.
1:30?
It was cold in the project.
Why do you want to do it earlier?
Maybe this one is
Yes, that's the point, yes. Okay, let's do it
but
1:30.
now it's perfect.
Well, that would work then, yeah? Yes.
This is just like 10 minutes walk from here, from East.
Slightly longer, and it's even better if you take a bicycle.
Yeah.
We have 2 bicycles which can be rented. My son's bicycle, which he also take. Yes. Okay, fine. Let's do that. So 1:30 then. Yeah.
Okay. And then, as I